This is EN2041 Thermodynamics. Lecture 2. This is our first lecture on reciprocating engines, and it forms 4 parts. And the main purpose of this lecture is just to introduce to you some of the concepts of reciprocating engines. So we're going to look at idealized cycles a bit later on in the module. We're going to start with real cycles in this one so that we can see how real cycles operate. Now that means that the thermodynamic analysis of real cycles is actually more difficult. So when we go into the ideal cycles, we do so because we can use principles which we can apply in a logical way and get good answers that allow us to calculate things like efficiency in a sensible fashion. So one of the reasons that this video has been recorded is for you to take part in what we call flipped lectures. Now a flipped lecture is where the material is actually given to you in a format like this, such as video, and you actually watch the lecture, and then when we get to the lecture session itself, we discuss the issues and the problems around this rather than me talk, you listen type format, which isn't as efficient as what we're doing now. So I hope you don't find this too confusing, but the purpose of today is just to go over the lecture material, and then in the lecture itself we can discuss what it actually means. Okay, let's move on and take a look at what we'll be studying. So the learning objectives, or what you'll be able to do after this lecture. First of all, you should be able to understand the concepts concerned with some of the thermodynamics of reciprocating engines, or at least you should be able to describe them in some fashion. So what you'll be able to do after this lecture is to discuss the real cycle in terms of a pressure volume diagram, and we'll see what happens with that. The next thing is you should be able to discuss some standard cycles and see how they differ using a PV diagram. We're not actually going to do TS diagrams in this lecture in particular. We're going to see TS diagrams later on when we do things like the Brayton cycle, when we look at gas turbines. And then the third thing is we're going to look at some of the modern concepts of engine designs and how these might have an effect on standard cycles. So my real aim for you in this lecture is for you to understand what some of the terminologies mean, look at some of the more modern developments. Direct fuel injection is a very good example there. We don't really use carburetors on modern low emission systems anymore, so we need to understand what direct injection is, and just some simple ideas like some engines are fueled on diesel, some are fueled on gasoline, some engines are 2-stroke, some engines are 4-stroke. It's that sort of thing that we need to know by the end of this. And then when you go into the next lecture, the lecture after this one, we'll do the more complicated thermodynamic analysis, but it means that you'll understand where we are. You'll be able to relate some of the more complicated things to the general operating principles of a reciprocating engine. Okay, so in the video that's about to follow, what we're going to watch is a Formula 1 engine being tested on a standard test bed. So what they do on these beds is they put the engines on, run them up and down. They'll subject them to different scenarios, possibly acceleration scenarios, maybe even going uphill, the sorts of things that you would expect to see if you were modeling or testing or inventing a new engine. And this is obviously a 4-stroke engine. It's fair enough, it's a very high performance system, but it'll give us an idea for what we're looking out for. So what I want you to do is kind of think like an engineer and observe and watch and listen and see what's happening to the engine. The most important thing I want you to understand from the video that's about to follow is the exhaust manifolds that you're going to see. You're going to see them glowing red hot. So if the exhaust manifolds are glowing red hot, what does that mean? Does that mean that there's an enormous amount of heat coming out of the cycle? If there is an enormous amount of heat coming out of the cycle, is that something we can use or something we can't use? Is that an opportunity to turn our fuel energy into work? Or is it symptomatic of fuel energy that has not been turned into work? It's been turned into heat. So if I'm an engine designer, and I could be designing a Formula 1 engine, or I might be designing something a lot simpler, maybe even an engine for a chainsaw, do I really want to be ejecting all of that heat, or do I have no choice? It's an interesting thing to think about. Now, we're not really going to analyze that until the next lecture, but look at all the heat that's pouring off this engine when it's operating. hopefully then you saw those exhaust manifolds glowing red hot, and it would start to make you think about efficiency and how much of the fuel is being turned into mechanical work and how much is being turned into heat. Now that's not the same thing when we talk about entropy and we talk about the inherent nature of energy loss as heat moves from one place to another. This is something different. This is about human beings trying to build machines that convert fuel energy into work, but they do it via heat energy. So heat energy is the thing that flows, and it's very difficult for us to recover all of that. And that's what we're going to look at later on in this part of this module. Okay, so let's start introducing a bit more notation and getting used to other things about engines. So we're going to split the engines into two. There's two main types of reciprocating engines, and I'm sure you know this, but all we're doing really is just cementing this idea in and just giving you some numbers to get used to. So the first type of engine is called a spark ignition engine, and there's every chance that you know all this, but that's okay. We're just making sure. So a spark ignition engine uses a fuel that's called gasoline. Okay, so you might be looking at the word petrol and saying, no, I use the word petrol, because we do in the United Kingdom, but mostly internationally, the word gasoline is used. So just for ease of notation, you'll only really hear me use the word gasoline. I won't say petrol. But just because it's more universal. So spark ignition engines use gasoline. That's what they burn on. Now they tend to use something called a spark plug to initiate combustion, and we're going to see something about that in subsequent lectures. And they have compression ratios which are in the range of between 7:1 or 10:1. That's what it's saying there in the brackets. So let's imagine that the compression ratio, we're going to keep it simple. Let's imagine that the compression ratio was 10:1. What that means is that when the cylinder is fully swept down, so it's at what we call bottom dead center, imagine that the cylinder's volume was 1 litre. When the cylinder compresses all the way up, so once the piston has traveled all the way to the top of the cylinder, then under a 10:1 compression ratio, your volume that's left in the top of the cylinder would be 10 times smaller than that. So that would be 100 milliliters. Okay, so that's what it means. That's compression ratio, and it works actually on volume. When we look at gas turbines later, we look at something called pressure ratio, which is different. That's the ratio of pressure before and after. In reciprocating engines, the terminology we use is compression ratio. It's based on volume. Okay, so now let's look at the other kind. So the other kind of engine is called a diesel engine. So a diesel engine is not named after the fuel on which it operates. Okay, so Diesel was the inventor, or is credited with being the inventor of this engine, of this particular type of thermodynamic cycle. That it's not named after the fuel. I say this because this is what I used to think when I was a student. That you know, diesel fuel goes in diesel engines. It does, but it's the fuel is named after the engine, not the other way around. So we put diesel fuel in diesel engines, and diesel fuel has something of a slightly wider molecular mass distribution, but it's also heavier. I've put that term in inverted commas there. Heavier meaning its average molecular mass is larger than gasoline. It's got quite different properties. It actually needs higher compression ratios to burn. That's one thing, and the other thing is that it's not as volatile as gasoline. So because you can squash it harder, you don't need to hit it with a huge spark. It will actually do something called auto ignition, which we're going to look at later in the module anyway. But I'll just leave you with that really. So the compression ratios in diesel engines are more like 12:1 or 20:1, and things are evolving and changing as we go forward. But they can have much higher compression ratios, and the reason they can, so you need to learn this now, the reason they can is because of the nature of the fuel that's being used in the engine. And as we're going to see in the fourth part, it's a bit of fun, but as we'll see in the fourth part of reciprocating engines, you'll find out that they're really not compatible. You can't put one fuel in another engine. You can't put gasoline in a diesel engine, as you're about to find out. All right, so the next thing I'm going to do is I'm going to split these engines into two again. So the first type of engine is called a two-stroke engine, and we'll see why it's called a two-stroke engine. We've got a nice video for you to look at in a minute. and we're going to contrast those with 4-stroke engines. Okay, so here's a picture of a 2-stroke engine, and you're going to see the video where somebody's going to explain it in a bit more detail as well in a moment. But with 2-stroke engines, they're much simpler to operate. They're much cheaper to build. We don't need as many valves. They tend to have pretty horrendous environmental performance, as we're going to find out in a minute. But what they are is cheap and simple to use. We can do all sorts of funny things with them. You're going to see that in a minute. But thermodynamically, in terms of our cycles, it's not a 4-stroke cycle. You might have learnt about 4-stroke cycles, possibly in high school. So you may remember suck, squeeze, bang, blow, which are the 4 colloquial terms for the 4-stroke cycle. But this a 2-stroke cycle is something quite different. It actually does 2 of the processes almost simultaneously. It's a bit more, best way to describe it, it's a bit more homogeneous, this cycle. Things tend to happen more gently, and things tend to happen at the same time, whereas the 4-stroke cycle is much more discrete and ordered. So it kind of induces the charge. This is the air and the fuel, and then it squashes it in one part of the cycle, and then the fuel burns and it exhausts in the other part of the cycle. So we have 2 things happening at once. Perhaps in some cases I should have put the 4-stroke cycle across first, because it's what people are more used to. But have a look at the video, maybe run it back if you're not entirely sure what's going on, but it explains it quite well. You have to see the direction in which things are flowing around the engine as well, but there's other online resources where you can see this and learn about this in other ways. So let's see it in action.
A 2-stroke cycle engine is used where low cost is important, such as in a power lawnmower. A cycle in a 2-stroke engine begins with the intake compression stroke. In this stroke, the piston moves up inside the cylinder. The motion of the piston sucks a fuel-air mixture into the crankcase for the next cycle and compresses the mixture already in the cylinder. When the piston reaches the top, the spark plug ignites the mixture. Burning gases push the piston down for the second stroke, called the power exhaust stroke. As the piston uncovers the exhaust port, the gases escape, and a fresh mixture enters the cylinder through the intake port.
Okay, that was the 2-stroke cycle. Now let's take a look at the 4-stroke cycle. Now you may be much more familiar with the 4-stroke cycle. In fact, the engine in the diagram on the right, which we're going to see another video for in a moment, that may look more familiar to you. It's got a spark plug in the right place, and it's got those valves in there as well. So you've got the inlet valve and the outlet valve. So this may look a lot more familiar to you. Certainly the more common kind of engine, as it says there, 80% of the engines produced in the world are in this kind of format. So it's a much more common system. So have a look in the diagram. You should be able to see that there's those 2. In this case, this is an overhead camshaft. So I'll just see if I can highlight with my pen. So we got these things up here. These are the cams which they actually act on the valve. So we've got the valves in here. The inlet is on this side, and then the outlet valve is the exhaust is on this side over here. So here's the piston, and then the actual the combustion takes place in this volume in here. So this is where the air is going in and out of. So down here in this part, we've got the flywheel in the crankcase, and the flywheel just keeps everything turning over with a little bit of momentum. I do get asked that question a lot by students, is why, why does the engine go the right way? How does it know to go the right way? It's actually continuously turning over usually, and there's a flywheel, which is a rotating mass. It's got its own moment of inertia, and then that keeps everything going round. So when you start the engine, you obviously start it in one direction and it keeps going that way. So we're going to see a little video. So we've got the 4-stroke cycle. So as I said, colloquially, or what we learn is suck, squeeze, bang, blow. But what we actually mean is induction, compression, ignition or combustion, and then exhaust. And those are the 4 parts of the cycle. We're going to look at them throughout the rest of the lecture in their real form, in their non-ideal form, and then when we do the analysis in the subsequent lectures, we will look at them in their idealized form so that we can do some thermodynamic analysis. So let's take a look at the video. Again, watch it carefully, make sure you know everything that's happening in there.
The engines of most cars operate on a 4-stroke cycle. During the 4 strokes of this cycle, a piston moves down and up inside a cylinder. Valves help control the flow of fuel and air into the engine, and the flow of exhaust out of the engine. The first stroke of the cycle begins with the intake stroke. In this stroke, the intake valve is open and the exhaust valve is closed. The piston moves down the cylinder, drawing in a fuel-air mixture. In the second stroke, called the compression stroke, both valves are closed. The piston moves up the cylinder, compressing the fuel-air mixture. At the top of the compression stroke, the spark plug ignites the mixture. In the third stroke, both valves remain closed. The burning gases push the piston down for the power stroke. In the final stroke, called the exhaust stroke, the intake valve is closed and the exhaust valve is open. The piston moves up the cylinder again, pushing the burn gases out.
Okay, so let's now have a look at the 4-stroke cycle in terms of a pressure volume diagram. How I like to introduce this to students is to firstly just show the whole thing, and then we'll step through each part individually nice and slowly so that we understand what's happening. All right, top right hand corner, that's a diagram of a modern 4-stroke engine. It's only got one set of inlet and outlet valves, but that's okay. It doesn't matter. It shows the concept very well. So we can see the crankshaft, the connecting rod, the piston, the valves themselves, the air and fuel inlet, and then the products or the exhaust, and the spark plug. We can see the camshaft as well. Everything you need is in there. That's what you need to know and understand about reciprocating engines, in this case the 4-stroke engine. All right, then let's have a look at the pressure volume diagram over on the left. It's a reasonably good representation of what happens in actual engines. Of course, they're all going to be a little bit different, but this is what we need to understand and take away from this. So it looks a bit confusing, looks like a funny shape. You can see there's a bit of a crossover in there. Let's just quickly orient ourselves with this, and then what we'll actually do is step through it in much more detail. Okay, x-axis is volume, isn't it? So as the piston goes up, the volume of the cylinder that is actually undertaking some kind of a thermodynamic process, that's going to go down, isn't it? That's going to reduce because we're squashing things down. So the volume, remember, volume is more of a mathematical thing. The volume is going to go down. Okay. Well, if the valves are closed when that's happening, I'm assuming the pressure is going to go up as well, isn't it? So think of it like that. All right, so then we've got pressure on the y-axis, haven't we? So as things are squashed, the pressure is going to go up, and as things expand, the pressure is going to go down. Now let's have a look at some vertical lines. There's a line that says TDC and the line that says BDC. TDC stands for top dead center. What that means is that's the upper limit of the piston's travel. Okay, so that's where the volume is obviously the smallest. Go over to the right, you can see one called BDC. That means bottom dead center. Bottom dead center means that the piston is at its lowest point in the travel, and obviously the volume that's available for our thermodynamic process is at its highest value. Okay, so you can just see what's going on in here. Let's start at a logical place. So start at 1, there's our intake. 2, we start to compress. 3, we get some combustion. Over past top dead center, right to the highest point of pressure, back down we come, expansion. 4, then exhaust starts. Okay, that's me stepping through it quickly. Now let's go through it in some much more elegant detail. Okay, so here we have the pressure volume diagram, and we have the first part in our 4-stroke cycle, induction. Remember, this is as close as the real cycle as we're going to get. When we do our subsequent thermodynamic analysis, what we're actually going to do is a much more simplified version. But let's get the real cycle done first. Okay, so induction. Air and fuel vapor gets sucked into the cylinder. So at the moment, we're not going to talk about direct injection. This is just what is referred to as a carburettorized system. So air and fuel gets sucked into the cylinder, and then at the end of that, the inlet valve is going to close, and that signifies the end of this part of the stroke. So let's play the animation. Off we go. There we have it. So you'll notice that the volume increased. That's logical. That's the volume in our cylinder, which is available for our process, is getting larger. Great. And the pressure dropped a little, not much. A small drop in pressure. That makes sense because the air is flowing from one reservoir to another. You don't get any flow without a drop in pressure. So as the cylinder is coming down, I guess it's sucking the air and the fuel in. Okay. Let's move on to the next part of the cycle. So part 2 to 3 is compression. So now the valves are closed. The inlet valve, the exhaust valve, they're all closed, and the cylinder is now being driven upwards. Let's go back to that question students ask me all the time. What's driving the piston up? I always get asked that question. Well, what's driving it up is probably the flywheel that's spinning round because the system was already operating, it was already in some kind of a steady state. Or it could actually be that there's more than one cylinder in our process and the adjacent one is driving it. But the easiest way of remembering it is that the flywheel's turning, everything's still moving, so it's being driven by the rest of the engine. Okay, so in compression, all the valves are shut, and what happens is our pressure starts to increase, but logically our volume starts to decrease as we start to squeeze everything together. Okay, let's watch that one. And up we go. All right, we're at part 3 now. Now the piston is still going to continue to move upwards, but what happens now is we get some combustion. Let's move on and see that one. So this is called the power part of the stroke. This is part 3 to 4. So we ignite the charge. So the fuel and the air are all nice and mixed now. They're ready to burn. So they just need a bit of energy to get them going. So we have a spark ignition in the case of a gasoline engine, but actually in a diesel engine, we don't need a spark. It auto ignites because the pressure gets so high. So the charge ignites just before top dead center, and we start to get some combustion. And in the case of a 4-stroke cycle for a gasoline engine, what we get is something called constant volume combustion. So the combustion process occurs whilst the piston isn't really moving. We're going to talk about that later anyway. We just need to get the shape right. So the piston does continue to move up a little bit, but then eventually what starts to happen is that it goes past top dead center and then it starts to move down, and it's moving down because we're now acting on the piston itself. There is heat release in our chemical reaction. It's an exothermic chemical reaction, and heat is being released. That means that the products of combustion are starting to expand. They're at a very high temperature and they're expanding, and they're pushing the piston out of the way. They're pushing it downwards. Let's watch that. Okay, there we go. So I coloured in part of it red because that's symbolising that the chemical reaction called combustion was taking place, and then the combustion kind of finished, but the gases are still hot, so they're still pushing the piston down. So we can see we're at 0.4 now, and what is ready to happen is that one of the valves can open now. So the exhaust valve is going to open. So from 2 all the way around to 4, all the valves were closed, and now it's time to open up the exhaust valve and let those products of combustion out of the cylinder. So this is the exhaust stroke. The exhaust valve opens just before bottom dead center. It allows things to keep moving. So it's all about timing, building an internal combustion engine. It's a bit like music. Everything's got to have the right kind of timing to it. So just before bottom dead center, we open up the valve, the piston starts to push things and everything flows out. So the combustion products are pushed out of the cylinder. And usually we leave, again, it's all about very careful timing. We might leave a tiny little bit of combustion products behind, just to dilute the fresh charge a little bit. There's whole other reasons for that, but what we're interested in is just the fundamentals. Okay, so then we're into the exhaust stroke, and let's watch that one on the animation. And there we go, everything out. So now the exhaust valve will close and the inlet valve will open and the process starts all over again. Okay, so that's the 4 strokes in the cycle. Now let's see if you are paying attention. It's important for you to be able to demonstrate understanding. So what I don't want you to do is I don't want you to try to reproduce this from memory. I don't want you to close your eyes and see the picture in your head. I don't want you to do that. That doesn't help you. What I want you to do is pause the video when you're ready and draw the pressure volume diagram of this cycle, but I want you to do it by deriving it for yourself, thinking about all the different parts that are happening. Now, I've done this in the lecture a lot with the students. It always surprises me how people just instantly become lost because they're probably trying to remember the picture. Don't do that. Just do it logically and think, okay, I'm going to start off and it's going to be the induction stroke. What would that look like? Once you've got the first part, the rest will follow, okay? So it's not confusing. If there's other people with you, then talk about it with them and try to understand between you what you think is going on. Okay, so maybe pause the video, have a draw. Don't cheat. Don't look at your notes or anything like that. It doesn't help you. I don't necessarily want you to get it right. I want you to think about it. That's the important thing. Okay, when you're ready, then we'll get going again. All right, so hopefully you drew your cycle diagram, you understood something about it, and you're feeling confident that you know what's happening. Okay, so let's look at something called the diesel cycle. So this is similar to the spark ignition cycle, but the pressures are quite significantly high. They're almost double in some cases. It's named after somebody called Rudolf Diesel. Rudolf Diesel was a very successful, a very intelligent inventor. What you'll find with my style of teaching is I'm always happy to talk about the history of these people because I think their contributions are significant, and I think they're worthy of us just looking very quickly into the history books and just understanding their lives and what they did. So, understand the dates on there. Think about when Diesel was alive. So 1858 to 1913, what was happening in the world and the things that human beings were developing. So Diesel's cycle didn't involve the use of a spark plug, because what we actually do is we leave it to the fuel and air to itself to ignite. So if we take diesel fuel and we squash it hard enough, it will start to burn. I don't need a spark. Now, we quite often have something called a glow plug in a diesel engine, and a glow plug is actually just a hot surface where we would like the combustion to start from, but it's not a periodic thing like a spark plug. We don't hit it with a spark every now and then when we want the combustion. We auto-ignite the combustion via compression, but we'd like it to start in the same point every time. It makes the engine run a bit smoother, really. So if you've ever driven a large diesel engine or a fairly old diesel car, when you get in them, you turn the key and a little light comes on, and it sort of is saying to you, hold on a minute, I'm just warming up. So what's happening is the glow plugs are warming up. With more modern engines, they tend not to do that, but that's how a diesel engine works. It needs a glow plug just as a starting point from the ignition. But normally they will actually they will just light up themselves on as long as the compression is there. So with diesel as well, fuel is injected directly into the combustion chamber. We don't use a pre-mixed charge. So the air is squashed, and as it's being squashed, we throw the fuel in as well, and we're going to look at some of that later on. Okay, so that's the diesel cycle. Let's just take another look at it in a diagrammatic form. So it's the same thing really, but what we need to understand is just there's a couple of subtly different things going on. So traditionally, in the case of the diesel cycle, 1 to 2 is induction, just as we've seen before. Same thing, increase in volume, decrease in pressure as the piston sucks in the air only. Inlet valve closes, and then off we go with the compression stroke. So the valves all close, the air pressure increases, volume decreases, and just as it's starting to happen, we then spray the diesel fuel directly into the cylinder. It does a couple of funny things, which we'll see later relating to direct injection. Things cool down a little bit because the fuel needs a little bit of energy for it to evaporate, so it takes the energy from the air, so things cool down a little bit. That's not really relevant. So let's watch the pressure increase. Up it goes, and at this point, at point 3, we don't hit it with a spark. What happens is it auto ignites. So the conditions are correct for the combustion reaction to kind of spontaneously start. We'd like it to start in the same place every time, so we have that little glow plug in there, that hot region inside the engine. Okay, there's the ignition, and then pretty much the rest of the cycle is almost the same. There we go, constant volume combustion. We're going to look a lot more about this when we actually discretely look at the Otto and the diesel cycles in the next lecture. All you need to remember about this one is no use of a spark plug and much higher compression ratio. So if I was to draw this diagram next to a spark ignition diagram, you'd see that the pressures would be a lot higher in this particular case, and the volume ratios as well, the compression ratios. Okay, let's finish off the cycle. And we've got the exhaust stroke. There we go. Everything is complete, just as before. So we're going to expand this a little bit into something called direct fuel injection. Now, the reason I'm teaching this is because pretty much every automobile that's being produced that has certain emissions regulations to meet, which you're going to learn about a lot later on, that's going to be in subsequent years and subsequent studies. One of the good solutions to getting around some of the emissions problem we have is to use something called GDI, which is it's gasoline direct injection. I was thinking DGI then, but gasoline direct injection is where we don't use a carburetor, and it's almost like a cross between the gasoline engine and the diesel engine. We still use gasoline fuel or petrol, and what we do is we spray the fuel into the combustion chamber as the cylinder is its volume is reducing. So as the piston is coming up. The gasoline is under very high pressure, and modern engines, the pressure is getting up to incredible pressures, hundreds of atmospheres, and in some cases on common rail systems they're even higher. So we have this common rail fuel system, so we've got a very high pressure pump driving all of this, and then a valve opens, it's squeezed through a very small orifice, and then we get a spray developed inside the combustion chamber. And if you thought that timing with valve opening and closing was crucial, this will probably blow your mind. It's really quite clever. We have very intelligent computers controlling a lot of this, and they can play tunes on it. So this is all about timing with this one. So the incoming fuel spray it goes into the chamber, and it actually cools the air. So the air's density changes, and it allows us to get a higher compression ratio. So we get better performance out of the overall engine. Might not make sense to you now, but it will do at the end of this part of the module. So what we end up with is a more efficient engine because we're cooling the air and fuel mixture as we spray the fuel in, because the fuel needs some energy to evaporate, and it gets that energy by actually extracting heat from the air that's being squashed. So it's more versatile, more controllable, and we can start to tailor things. So we can have variable valve timings, but we can also have variable injection quantities, all clever stuff. And this is something that's quite a lot beyond the remit of this module, but it allows you to see where things are going in the future, or at least where current trends lie. So I'm going to show you a video. It's It's actually quite an old video. It's produced by a US engine manufacturer. It's always worth a bit of a laugh when they talk about the actual miles per gallon, the fuel consumption of the cars, because modern very small engines will kill that. You'll do double what they're saying in this video. But it really explains what's going on. There's some fantastic animations in here, and it allows you to see GDI in action. So let's just have a quick look at the diagram on the right. But I think the video says it all. So we've got our spark plug in the middle. We've got some valves in there. So we've got our inlet valve and our exhaust valve, pistons in the usual place. And then you can see that on the left side, there's this fuel injector. It's a direct fuel injector, and it allows the fuel to go straight into the cylinder. So we're not pre-mixing. So there's all sorts of issues with getting that fuel in the right condition to burn, but that's beyond this module. What we're really looking at is this is how a GDI system works. This is what one looks like. Okay, let's take a look at the video. My main interest in this video is actually just the animation itself, but you can see what's happening here.
Direct injection, or DI as we refer to it, is a really cool new technology that we're using to increase the fuel efficiency of our engines, but at the same time increase power and lower emissions. In the direct injection engine, we spray the fuel directly into the combustion chamber, which allows us to cool the intake charge. Therefore, we can increase the compression ratio in the design, and that's how we get the increased efficiency to run better fuel economy, more power, and cleaner emissions. Think about the Cobalt SS for a second. 260 horsepower, 0 to 60 in 5.7 seconds, and 30 miles per gallon on the highway. V6 power with a 4-cylinder fuel economy. Direct injection helps make this possible, and we can do it without adding a lot of extra cost to the vehicle.
What I'd like to do now is go back a step, and we'll look at the difference between 2- and 4-stroke engines, and then we'll leave it there pretty much for this part of the module, so that we can start looking at thermodynamic analysis and idealized cycles in the next one. So let's just make sure that we understand the difference between a 2- and a 4-stroke cycle. So a 2-stroke cycle needs fewer valves. So go back to the diagram and the video, and you'll realize that in many cases you can almost get away with no valves at all. What you actually need is a hole in the side of the cylinder, and the piston head itself actually forms part of the sealing of the process. So it's quite good in that respect. And it can actually run in any direction. So something to do if you're ever that way inclined. You can sometimes get hold of 2-stroke engines for running things like golf carts. So yeah, if you push them backwards, they'll go in any direction. It doesn't really matter, because the timing is not as intricate as a 4-stroke cycle. So lots of fun in your spare time if you've got access to that kind of thing. So actually, if you have a 2-stroke engine that has a gearbox, you could actually run it in reverse direction and cycle through the gears in the same way. It doesn't really matter. It's not crucial about valve timing and all that kind of thing that you get with a 4-stroke engine. The other thing that you'll get with a 2-stroke engine is that the power for a given weight and size is a lot greater for a 2-stroke. So, and we get much more uniform torque. We can have a smaller flywheel, because the system itself is actually inherently much simpler. And it almost sounds like 2-stroke engines are the way to go. You know, in many respects they're far easier to construct. They'll be cheaper. In many ways, they might even be more reliable because there's less things to go wrong. So there must be something in 4-stroke engines, or otherwise, why would we 80% of our engines be 4-stroke? Okay, so here's the downside. 2-stroke engines will have much higher fuel consumption. So I want you to think about that for a minute. Why would they have much higher fuel consumption? What's that relating to? Has it got something to do with the fact that if the engine is, or if the piston is moving and as it goes down, it opens up a valve, or it opens up that orifice to let the exhaust out, the combustion could still be taking place and things get discharged out of the engine whilst they're still half burning. Okay, so that might make the fuel consumption higher. What on earth would that do to the emissions? What would the emissions from a 2-stroke engine look like compared to the controlled very highly coordinated four-stroke engine where the valve doesn't open until we're sure that everything is finished, you know, that sort of thing. So we get really bad exhaust scavenging like that, and actually some fuel just goes straight through the combustion chamber. It doesn't get the chance to burn. It's actually burning on the way out. So imagine what kind of a noise a two-stroke engine is going to make. We'll actually see in a minute because we've got a video comparing the two together. The other thing is that with two-stroke engines, the oil is also in direct contact with parts of the process. So the air rushes over the crankcase as it comes in, and in doing so, it's going to pick up a bit of oil with it. So we're going to have a high oil consumption. We're also probably going to have oil combustion that gives us even more smoke. So these things actually are inefficient. They're filthy, dirty. They're noisy. They make a bit of a weird whining noise, as you're going to see in a minute. So they're very much, here's an interesting term to use, they're very much under-engineered, whereas a four-stroke engine is much more precise and it's much more bespoke for the problem in hand, whereas two-stroke is cheap and dirty. So given the fact that there's so many environmental legislation flying around at the moment, two-stroke engines have very, very limited areas of operation. So in this next video, it took me a while to find this because I was curious to see if anybody has really compared the sound of these two engines. So we got a bit of an amateur enthusiast here, a young chap from the US who's very proud of his two motorbikes. And at the time, this is the only thing I really could find on the internet where somebody had done this, so good for him. What he wants us to do is listen to the sound of the two motorbikes and tell us, we can tell him what we think. I'm really more interested in, given the fact that the two motorbikes are a very similar design, they've got almost identical engine size, so the amount of volume inside the cylinders is pretty much the same. The compression ratios are probably comparable as well. But what we have is one is a four-stroke and one is a two-stroke. So listen to the difference in sound between them, and maybe discuss with your friends or consider what it is that's actually making them sound differently. So you know the difference between the two designs of the cycle. You know what's happening here. So how does it sound? Now there'll be lots of other irrelevant things which are happening in these engines as well, possibly to do with the exhaust systems. Okay, I understand that, but you can certainly hear that they're revving, or they're turning over. Their revolutions per minute are completely different because of the way in which they're designed. So that's something you can think of. But also going back to what I was saying about how the two-stroke engine, parts of the process are happening simultaneously. So it's almost like ripping open the cylinder whilst the combustion process is happening. Actually takes place more in a two-stroke engine. So this is almost a bit of fun, but it allows you to appreciate or to experience the difference between the two. And then what I want you to try to do is relate to the science that we've already covered in this lecture. So let's have a listen to these, and then we're pretty much done with the theory in this part.
These are my two dirt bikes. This one is a Honda XR80. And it's a four-stroke, and this one is a Yamaha RT100, and that's a two-stroke. So I want to see which one that you guys think sounds better. We're going to start off with the 80, it's four-stroke. That was the four-stroke. Now we're going to move to the two-stroke, the Yamaha RT100.
Okay, that's the end of the content that we need to understand for this session. So just a simple introduction to give you perhaps some of the nomenclature for the different parts of reciprocating engines, so that when we do the thermodynamics, it means something to you. It's not just a bunch of very dry looking diagrams in a textbook. So when you look at what we're going to do next is the Otto cycle and the diesel cycle. When you look at them, they're not just going to look like boring, meaningless boxes with arrows all over the place. You're going to be able to relate them to things which are actually real. That's the purpose of this session. So if we're doing this as under flipped lecture conditions, then you watch this and we'll come into the hour-long session in the appropriate lecture 2. And what we'll actually do is talk about what it all means and how we can relate it to thermodynamics. Then when we do the thermodynamics, hopefully it all makes sense. Let's find out. Okay, what have we seen? The difference between spark ignition and diesel engines, and the difference between 2-stroke and 4-stroke engines has all been made clear to you now. We've looked at pressure volume diagrams, but the pressure volume diagrams have been used based on something that's close to real cycles, and what we'll do next is on ideal cycles. But it shows the characteristics, doesn't it? It shows the induction, the compression, the power stroke, and then the exhaust at the end. So we've seen all of these things. You should know what they mean. What we'll look at next is idealized, so that will be Otto and diesel, and it will allow us to then extract some useful parameters. So perhaps one of the things you could consider is how on earth you would do a thermodynamic analysis on the quite complex looking diagrams that we've seen in this lecture. Bit too difficult, a bit too many things happening at the same time. We'd need equations to relate the enthalpy of combustion and the heat transfer processes required where things are going along simultaneously. It's not helpful to us. What we would like to do is approximate this process, and then in doing so compare one thing to another. So compare one engine to another and learn about the limits of the processes, and that's the crucial thing that we're going to learn about in the lecture that's coming. Not next, but the one after that. We'll learn to differentiate between what's happening in the different engines and how we can optimize them and what their limitations may be. And because we understand those limitations, then we'll be able to say meaningful things, not, oh, I wish we could make engines more efficient, but there's things holding you back, you know, and I wish we could make these engines perform better, go faster. It's not as simple as that. We have to look at the underlying thermodynamics first, and that's what we're going to do next. So make sure you understand everything in this session. Let's now have a discussion about this in the lecture. I'll ask you some questions. I'll get you to think about the significance of it all, and then we'll be in a good position to analyze those PV diagrams, and they're not just meaningless squares and arrows and things like that.